Hey everybody, the lecture I've got for you today is on 8.3 in AP Chemistry, which is weak acid and base equilibrium. So let's go on ahead and jump right into it. So just like I've done with all my other videos, these are all the things that you need to know before you're done with this unit. Little learning checkpoints that if you can do, you should be pretty good for the AP exam. So if you want to pause this and look at what you should be able to do, go ahead and do that. So to start off, I want to give just a couple reminders of some things. First off, what is an acid? What is a base? So an acid is a substance that donates a proton. And if you remember, a proton is just listed as H+. It's hydrogen that's lost one of its electrons. So it's just a proton. And an acid gives up one of those protons to something else. So for example, right here I have HNO2, which is nitrous acid. And it's giving its proton, giving its hydrogen to the water. When you do that, you form what's called the conjugate base, which is just the acid with one proton lost, and you take the base and make a conjugate acid, which is the base with one extra proton added. Okay? A base is a substance, I know my head's kind of blocking it here, but if an acid is a substance that donates a proton, excuse me, a base is a substance that accepts a proton. So here I have ammonia, NH3, and what you see happening is it's mixed with water, which in this case is acting as an acid. And so the ammonia is taking a proton from the acid and making NH4+. So you have the base, ammonia, and the conjugate acid, NH4+. Then you have water, which is the acid in this case, gave a proton to ammonia, and so you have the conjugate base. So it's just the acid with one less proton. Now, we talked in some of our previous lectures, those of you that are actually in my class, about the difference between a weak acid and a strong acid. A weak acid is an acid that when you dissolve it in water, only a small amount of it ionizes, only some of it dissociates. So if you were to throw, for example, 100 grams of acid into the water, maybe only 10 grams of that acid actually dissolves in the water. The other 90 grams are still floating around as fully protonated acid. Okay? There are 6 strong ones in AP Chemistry. That's HCl, HBr, HI, HCO4, H2SO4, and HNO3. If it's not one of those 6 in AP Chemistry, it's a weak acid. Are there stronger acids than that out there? Yes, but in AP Chemistry, those acids are the only ones that we worry about that are considered strong. Everything else, it's weak if you don't see it. And an important point about this is if it is a weak acid and it only partially dissociates, that means you're in equilibrium. It's not a full dissociation where 100% of this gives up its proton to the water and turns it into hydronium. It is an equilibrium, which means that we're going to be able to write equilibrium expressions for it. So I know you guys are probably tired of seeing all the equilibrium constants because I know there's a lot of equilibrium constants. We went over a lot of them in Unit 7. We talked about Kc, which is the equilibrium constant with concentration, Kp, the equilibrium constant with pressure. We talked about Ksp, the solubility product. We even last lecture talked about Kw, which is the equilibrium constant for the autoionization of water. Well, here's another one. This is Ka, still an equilibrium constant, still calculated the same way as any other equilibrium constant. Okay, it's called the acid ionization constant, and it's basically a measure of how strong this acid is. If the Ka is larger, that means you have a stronger acid. If you have a small Ka, that means you have a weaker acid. And to calculate this is just like any other equilibrium constant that we've done previously. I know my head's kind of covering up, so I'm going to read this one off. I'm going to write this one out. So the Ka in this case, it's still products over reactants. So I have one aqueous product, which is the concentration of H3O+. Here's another one, concentration of A-. And then you have HA that's aqueous, so the concentration of HA. Now notice that none of these guys get an exponent. They're all just exponent of 1 because all of their coefficients are just a 1. The reason I don't include the water in this equilibrium expression is because, remember, pure solids, pure liquids are never included in your equilibrium expression, so we don't put it there. Okay? Now, these are weak acids, which means their Kas are typically really, really small. Okay? So what we tend to do as chemists is instead of reporting Kas, we tend to report what's called a pKa. And if you remember from last lecture, pH is the negative log of the concentration of hydrogen. Well, pKa is just the negative log of the Ka. And when you do that, you get a much easier to deal with number. And it's actually flipped because it's negative, whereas Ka, the larger it is, the stronger the acid. With pKa, the smaller it is, the stronger the acid. So it actually mimics like pH. The smaller the pH is, the stronger the acid. The smaller the pKa is, the stronger the acid. Just like a weak acid, weak bases are ones that don't pull off 100% of the protons that they could pull off. Okay, so for example here, if I have B as a base and it's trying to pull a proton off of water, it's trying to pull a proton off of water here. Well, it can do that. It can pull the proton off, kick those electrons there, right? And when you do that, you're going to form your conjugate acid, the Hb plus and the OH minus, right? Well, if it were a strong base, then a strong base would pull off as many protons as it possibly could inside of the water. Weak bases either don't pull off all the protons that they could, so if there's 100 grams of base, maybe only 50 grams of the base actually pull a proton off. Another way to think about a weak base is that it doesn't fully dissociate in water. So for example, a strong base, like for example NaOH, is going to dissolve completely inside of water. So 100% of it is going to dissociate. But if you have a weak base, maybe like 10, 20, 30% of it is actually going to dissolve inside the water. So just like a strong acid doesn't fully dissociate, a weak base doesn't fully dissociate, or a weak base, 100% of it doesn't pull off all the protons that it could. Just like Ka, there is also such thing as a Kb. Okay, my head's not covering it up as much, so you can kind of see the Kb expression that I have down here. Kind of see the Kb expression that I see down there. Works the exact same way like a Ka. It's just instead of being an acid dissociation constant or an acid ionization constant, it is a base ionization constant. Works the exact same way, calculated the exact same way, and much like a Ka, instead of using Ka as our measure of acid strength, we use pKa. Just like that, we're going to use pKb most of the time here because it's a much easier to work with number. For bases, the larger the pKb is, the weaker the base. The smaller the pKb is, the stronger the base. Okay, works the exact same way as pKa. Smaller it is, the stronger the base or the acid. So we've talked about how a strong acid is going to 100% dissociate in water. So you're going to have free ions. If you have HA, it's going to break up into completely H plus and completely A minus 100%, right? Well, a weak acid then is not going to break up 100%. The question is, how much is it going to break up? Well, chemists measure that with something called percent ionization, and the way that works is you calculate the concentration of the H3O plus, which is the same as the concentration of H plus in solution, at equilibrium, and you divide it by the initial concentration of acid that you had. Multiply that by 100, and you get the percent ionization. The more or the higher the percent ionization you have, the stronger the weak acid is. I know that's kind of hard to say out loud, but weaker acids, some are stronger, some are weaker, right? So the stronger the weak acid is, the higher percent ionization you have. And we'll do a practice problem in just a minute on how you actually calculate that. So again, this is dependent on the strength of the acid. If acids are of equal concentration, the weaker acid is going to have the lower percent ionization. If two samples of acid are of different concentration, the solution of lower concentration will have a higher percent ionization. And again, we'll do a practice problem in a second to understand exactly how that works. So this right here is just an equation sheet for you. I know my head's covering up one part of it, but the one where my head's covering that up is just the pH plus the POH are equal to 14. I have that in previous lectures for my kiddos. This equation sheet right here, if you want to pause this, take this down, use it as your own equation sheet. This is basically all the equations you're really going to need for this unit, other than one which we'll get to in 8.9 called the Henderson-Hasselbalch equation. But this right here is the main things we're going to need, at least for this unit. So if you want to pause, write some of these down, or come back to this so you can use it and you can try the problems on your own, please feel free to do so. Okay, now let's actually run through a couple of practice problems together. So this one right here says the pH of a 0.036 molar nitrous acid solution is measured as 2.4. calculate the percent ionization for nitrous acid. Okay, well, the first thing, at least what I'm always going to do, is I want to write down my formula. And so I'm going to say the percent ionization, and I just abbreviate that as percent ion, is going to be equal to the concentration of hydronium, or the concentration of H+, at equilibrium, divided by the initial concentration of my acid, so HA, or HA initial, times 100%. Well, do I know what the concentration of H+ is? Right now, no. But I do have the pH, and I can use the pH to get my concentration of H+. So what I'm going to do, I'll erase this first. What I'm going to do is I'm going to use my pH to figure out, well, what is the concentration of H+. And so I'm going to say, well, my pH is equal to the negative log of the concentration of H+. That's going to be equal to, in this particular case, 2.4. So I'm going to divide both sides by a negative. So I divide both sides by a negative. It's going to get rid of my negatives there. Log of the concentration of H+ is going to be equal to negative 2.4. And then to get rid of this is log base 10. So to get rid of that, I have to make 10 my base. In other words, this becomes an exponent, and this becomes an exponent. And so the 10 log right there cancels out. My concentration of H+, which I'm going to do up here, is now going to be equal to 10 to the negative 2.4. Okay? So now what you can do, you can pull out a calculator and you can say 10 to the negative 2.4. And what you get right there is that the concentration of H+ right there is 0.00, we'll say, in this case, we'll just round it up to make our math easier, 4. It's really 0.00398, but just to make our math simpler, 0.004. Close enough, all right? So now to calculate percent ionization, we're just going to use the same formula that we had a second ago. And so we're going to take our percent ionization formula, and we're going to say, well, the percent ionization is going to be equal to the concentration of H+ at equilibrium, which in this case is 0.004 molar. Should probably put that that's molar, divided by the initial concentration, which is 0.036 molar, and then we're just going to multiply it by 100%. And whatever that comes out to is our answer. So we'll take 0.004, we'll divide it by 0.036, and then we'll multiply it by 100, and rounding, we're about 11.1%. So really, pretty weak acid overall. So what I'm going to have you do is I'm going to leave this question right here. The pKa of hypochlorous acid, HClO, is 7.54. What's the pH of a 0.100 molar solution of HClO? I'm going to leave that to you guys to try to figure that one out. Specifically for my kiddos in my class. For those of you that are taking my class, I suggest you try this and then come talk to me about it and see how you did. I'll give you a couple pointers on some things. One thing I suggest you do here is you're going to want to use an ice table. You're going to want to use an ice table for this, okay? And remember that to get the pH, you're going to have to take the negative log of the concentration of H+. Okay? So that's what I'm going to leave you with for you to try. For anybody that's watching at home or any of my kids that are in my class, go on ahead and try that problem. Come back and talk to me about it and see if you can do it. And if you have any questions, please feel free to leave those in the comments, and I'll be happy to answer them. Thank you guys for listening, and I'll see you next time.